We are presenting over the nitration of acetanilide. The objectives of the experiment is performing a successful nitration of acetanilide using glacial acetic acid with a mixture of nitric acid and sulfuric acid to make para-nitro-acetanilide as well as ortho-nitro-acetanilide. Our other objectives is to calculate mass, percent yield, and also determine IR spectroscopy. To give a little bit of insight about the experiment itself, it's an aromatic electrophilic substitution reaction where an electrophile is going to replace a hydrogen on the ring, and the high electron density of the ring is going to attack the electrophile. From here, we see an intermediatory carbocation stabilize through resonance, and then a base is going to remove a proton from the carbocation, and this is what makes an aromatic ring. The substituent that is attached to the aromatic ring is where we see things like a reaction rate affected, orientation of a product affected, and we also see activating and deactivating substituents. More about our reaction in specific. Acetanilide is a nitrogen bonded. It also has 2 free electron pairs, and this makes it an activating substituent. The substituent is an electron donor, and it's why we see the ortho-para orientation come into place. To give a little bit about the procedure, we're going to use 6.5 grams of acetanilide and put that in a 125 milliliter beaker with 10 milliliters of glacial acetic acid. From here, we're going to use a steam bath. We're going to put those in there, and we're going to let this dissolve fully. Once this is dissolved, we're going to move and put it into an ice bath for 1 minute. After 1 minute has been reached, we're going to use 10 milliliters of sulfuric acid and keep this in the ice bath. We're then going to move this ice bath with the mixture we just made and move it to a stirring plate, let it stir for a little bit, and then add our mixture of nitric acid and sulfuric acid into our solution at a rate of 1 milliliter per minute. Once this reaction has fully taken place, we're going to take our solution and mixture out of the ice bath and let it sit at room temperature, but continue stirring for 30 minutes. After 30 minutes is done, we're then going to move on and move our solution we just made into a clean 250 milliliter beaker with 100 milliliters of cold distilled water. After this, we're going to start filtration. Our solution we just made, we're going to vacuum filtrate, and we're going to press and remove out any excess mixture with a beaker, pressing on top. After this filtration has been done once, we're going to take the filtrate we just made and we're going to move it to another clean 250 milliliter beaker and add again 100 milliliters of cold distilled water and let this stir for a little bit. After the process of stirring, we're going to filtrate once more, and we're going to add 2 sets of 30 milliliters of cold distilled water and then a last set of 50 milliliters of cold distilled water, really working out any of the excess solution and water that we have left. And then we're going to take our product and let it dry, and this is when we would take yield and IR spectroscopy.
Okay. So just so y'all kind of get a general idea of what's actually going on in this reaction, we provided the mechanism here. Now, I don't know if y'all can see this from all the way over there, but this top reaction says HNO3 plus H2SO4 gives us NO2 plus. What actually happens here is a proton from this acid, H2SO4, will be donated to one of the oxygen on the HNO3. When this oxygen picks this proton up, it will actually cause it to be unstable, and this will leave in the form of water. When this occurs, what we're left with is NO2 plus and water. Now to our actual mechanism. Here we have our acetanilide that we're trying to nitrate. Now, this bond on our benzene ring will attack the NO2 plus. Now, the reason that it's this bond and not any other bond is because the substituent that we're trying to add is place determined by what group is already attached. This group that's already attached is an activating group. Thus, our substituent will either add in the ortho position, which will be here and here, or the para position. As you can see here, what I have is p-nitroacetylenide, or the para substituted. That's because para substituted is the most prevalent in our reaction. This is because steric hindrance is going to allow for mostly para substituted because that's where it's least sterically hindered. Once this double bond is broken to attach to this NO2+, this double bond comes down to satisfy the plus charge that's created here, and then these electrons on this nitrogen atom will do the same thing. What you're left with is going to be these different resonance structures. This is actually why activating versus deactivating causes for ortho and para or meta. Deactivating would cause for meta, activating would cause for ortho or para. As you can see here, these are the resonance structures for para addition. The plus charge can either be here on the nitrogen atom, as we said, which will happen up here according to this mechanism. The plus charge can be here or here. Now these resonance structures are all very stable. So to actually get back to our final product and reestablish this benzene ring that we have, this HSO4 negative that was left with from up here will come in and pull a hydrogen off of this carbon that the NO2 attached to. When that happens, this HSO4 will pick up this hydrogen, and the bond that was attached to the hydrogen will go back into the ring and thus stabilize it, canceling the plus charge on it. Thus we're left with p-nitroacetylenolide. Okay, so here we have our data and our results. As Ashton said, we used 6.5 grams of acetylenolide and 10 milliliters of glacial acetic acid. What we produced was 35.84 grams of nitroacetylenolide, and our percent yield was 411%. To get these numbers, these are our calculations. First, to determine the theoretical yield, we took the grams of acetylenolide and converted it to moles of acetylenolide times the molar mass of acetylenolide to convert it to moles. And then we converted that using the molar ratio that we got from our balanced chemical equation to convert it to moles of nitroacetylenolide. And then we converted moles of nitroacetylenolide to grams using the molar mass. Thus, what we were left with was 8.7 grams, roughly. So that is about how much that we should have produced. To determine how much we actually produced, we took the weight of an empty watch glass and subtracted it from the weight of a watch glass with our product on it, as you can see here. This was the weight of a watch glass with our product on it, minus the weight of our empty watch glass. Thus, we produced 35.84 grams. To kind of get a ratio of how these two compare, we calculated our percent yield, which is our actual over theoretical. And what we were left with was 411.58%. And lastly, the last part of our data, we took the IR spectroscopy. From this, we were able to determine that we did successfully produce our target product. From what you can see here, these are our C bonded to our H's, single bonded to our H's. Here, this bond around 1750 shows our C double bonded to our O. These little bonds right around 2000, these little dips, prove that we have an aromatic compound. And this long peak right around 1500 is our NO bonds.
Okay, so to conclude our experiments, our group can successfully say that we nitrated the acetanilide and created nitroacetanilide. As Brody just showed you on the data results, our IR does confirm that for us. We have an aromatic compound around 2000, the ring that is. We have our C double bond O's at around 1750, and we have our C H bonds at around the 3000 mark. Also, as you saw with Brody, we had a 411% yield, which is not ideal, but we believe that is a result of not recrystallizing after filtrating. So who knows what could be left in there? Who knows what was in there? Who knows what it would have been had we recrystallized? So if we were to do it again in the future, we would make sure to recrystallize. So for post-lab questions, we have 3 questions. Number 1 is, the nitration of acetanilide requires the use of a mixture of HNO3, H2SO4. Why can't we only use HNO3? Well, we need the H2SO4 in the mixture because that is what is going to create our nitronium ion. It's going to take an O and H off of the HNO3 to make our NO2+. Our NO2+ is the electrophile, and if we don't have an electrophile, we don't have a reaction. So that sulfuric acid is very important to create that nitronium ion. Number 2, why must a nitration reaction be carried out in an ice bath at all times? Well, this reaction is very unstable, very reactive. Keeping it in an ice bath keeps it calm and cool. We don't want it burning up our products or burning up in general. Keeping it in an ice bath basically saves and preserves the reaction. Number 3, in the nitration of bromobenzene, what are the expected structures? Write the reaction. So we are going to have bromobenzene plus HNO3, H2SO4, and we're going to create both the para and ortho 1-bromo 2-nitrobenzene. Because we're using bromine is a halide, which means that it is a deactivator. And what we know about deactivators is that we're going to para and ortho substitute. So I think that's it. We have our references next. And thank y'all.